All right. Hello, everyone. Welcome to the 58th online Spintronics seminar. It is my great pleasure to introduce our speaker today. Dr. Hu is a professor at the University of Manitoba in Canada. He graduated from Fudan University, received a PhD from Würzburg University, and got the habilitation degree from the University of Hamburg. In 2018, he was an IEEE Magnetic Society's distinguished lecturer, gave more than 50 talks on cavity spintronics around the world. In 2019, he was elected as a fellow of the American Physics Society for outstanding contributions to the fields of cavity spintronics and Kvt Magnolic. This talk is going to be focusing on the same topic. So without further ado, Professor Hu, please take it here.
Thank you. Yeah, thank you, Xin. Thank you, Cleo, for giving me this opportunity to talk about our research. And also, I should thank you for really organizing this wonderful thing. It's a great thing that you guys is doing for the community. And I'm also very glad to see many names of my old friends. I just want to say hi to you guys and hope all you guys are doing well during this pandemic. And I hope that very soon we can meet again and celebrate different things. So before I start, I should first thank my students. They have done the work that I'm going to present to you. Ying and Jingwei, these are two PhD students. Yongsen is a research associate. And there are students and the postdocs already finished the training, left my group, leading their own group now, doing different research. And also I should thank the funding agency, NSEC, the Canadian NSF, funded many part of research. So why Kvt Magnolic or Kvt Spintronics? Well, people have always been interested in studying the coupling between photon and the spin. If you couple the photon to one spin, then this coupling rate, also known as Rabi frequency, is very low, typically at the 1 Hertz order. In 2010, Michael Flatte proposed that if you replace the single spin with a collective spin excitation, the magnons, then the coupling rate will be significantly enhanced by a factor of square root of n. N is the number of the spins in your system. Because in the materials, the n can be very large, you can expect a significant enhancement of this Rabi frequency. Michael predicted for macroscopic ferromagnetic samples, if you put in a cavity, then the Rabi frequency can go as high to terahertz. So people get very interested in that, and quite a few groups started the experiment around 2013, 2014. The first group reported this type of magnon-photon coupling from Hans Huber in Munich. And here are two examples of this kind of coupling. This one, what you see here, is done by Nakamura's group at the quantum regime, low temperature, single photon couples to the magnon system. And you can see this gap induced by the coupling is at the order of 100 megahertz. And we have also done some experiment, and we did the experiment in the classical regime at room temperature. And basically you see the same feature of the coupling, anti-crossing, with a gap typically at the order of several hundred megahertz. Indeed, quite strong coupling. And the physics of that is basically simple. And what you need to do is that you take a piece of macroscopic ferromagnetic sample, put in conventional microwave cavity. Then you have cavity mode as if it is one oscillator. You have magnon modes as if it is another oscillator. and the two oscillators will be coherently coupled. Coherent coupling means during the coupling, there is no energy loss, so that the consequence of coupling is introduced coherence between these two dynamic process, the phase correlation, so to speak. If you measure the transmission of that system, what you see is a Kvt mode, which is independent of the magnet field you apply. If you're changing the magnet field, you can tuning the frequency of the Magnum modes. Once the frequency of the Magnum modes approaches the Kvt modes, you see this typical anti-crossing type of behavior. As you are familiar from the coupled harmonic oscillator, you produce a hybridized mode, and the gap between them, as you can see, is typically at the order of several hundred megahertz. And the coupling basically produce a hybridized particle, a quasi-particle, which we now call it as Kvt Magnolic Polariton. This particle serves as a very good connection, because of the strong coupling, a very good connection between photon system and a magnon system, a transducer between these two systems. And of course, each of these photon or magnon system can be further coupled to many different other systems, so that this coupling becomes very useful in many different situations. For example, you can couple it to qubit, you can couple it to optical photon system, you can use it to connect different spintronic devices remotely, and so on and so forth. And I see some people, my friends, are in the audience, and perhaps you have also done this kind of experiment in the last few years. Please forgive me that if I didn't list your work. This field is really developing very, very fast, and there are lots of work coming in that direction. But what I want to focus in today's talk is not this coherent magnon-photon coupling, like the spring force couples to oscillators, but rather I would like to introduce you this dissipative magnon-photon coupling. And in fact, if you couple magnon and photon with both coherent and dissipative coupling, then you can produce some wonderful effect. For example, one effect I'm going to introduce to you is that you can produce a kind of microwave diode. Means for this kind of device, you are able to send a microwave from one direction to the other, but the microwave coming from the opposite direction will be completely blocked due to this kind of coupling. And I will explain to you how it works. But first, let me explain to you what is dissipative photon coupling. And I'm sure you are all familiar with this experiment we typically do for the first year physics or second year physics. If you take a piece of magnet and drop it inside a copper tube, then what you see is that this magnet will falling down very slowly, as if there is some kind of frictional force prevent it to doing free fall motion. And indeed, there is the frictional force, and we know that is due to the lens effect is going to induce current in the copper tube, and the effect is trying to against the change of magnetic flux, which means against the motion of the magnet. Now, with that, you can do a Gedanken experiment. Now, imagine that this magnet is not just falling down, but rather it is oscillating up and down in an oscillating way. Of course, that is also going to induce the current in the copper tube, and the current will be also oscillating. Now, these two oscillators will now be coupled by a kind of frictional force, no longer this spring force. And this kind of experiment you can actually do in the lab, because if you put a YIG, ferromagnetic material, inside a metallic cavity, and you drive the magnetization doing the ferromagnetic resonance or Lamotte procession, essentially you are producing an oscillating magnet macroscopically. And this oscillating magnet should induce oscillating current in your metallic cavity, and the two of them will be coupled by frictional force. And that is what we're going to call as the dissipative magnon-photon coupling. So how does it look like? Where you can simply model this system. Imagine you have one oscillator and a second oscillator. They are coupled by spring force as well as a frictional force. For example, you can build a dashpot between these two oscillators. Then mathematically, these two oscillators are coupled. One term is the spring force that is proportional to the displacement. The other term is this frictional force that is proportional to the velocity, which means the derivative of the displacement. Then you get this coupled matrix describing two oscillators with two different frequency, two different damping rate. They are now not only coupled by the spring force, but also coupled by this frictional force. And between these two forces, you see a phase difference of half pi because the velocity differs from the displacement by a phase difference of half pi. Now you can very easily solve this coupled system. And of course, if the spring force is dominated, then you see this very conventional anti-crossing type of structure for the eigenmodes. And you see also the damping rate of the system. We're showing this crossing or attraction, exchanging the damping between these two oscillators due to this coupling effect. This is the conventional coherent coupling behavior. Now, the dissipative coupling looks very interesting. And in the case you just set your model that this dissipative coupling strength is larger than coherent coupling strength, then what you see is this eigenfrequency showing attraction and crossing feature, but the damping now shows this anti-crossing and repelling kind of feature. And this is the behavior of dissipative coupling if you have two oscillators coupled by frictional force. Now, experimentally, we discovered this phenomena around 2018 when the students did the experiment by putting ferromagnetic material YIG inside this type of spatial cavity. This cavity is a bit spatial because it contains the standing waves due to the transition of this circular waveguide connected with rectangular waveguide. You have back and forth reflection of microwave forming standing waves. Take a cross section here, you see the standing wave patterns here. This is the node position, this is anti-node position, this is node position of the microwave magnetic field. In addition, this kind of wave allows traveling waves leaking through the waveguide. So it has two types of waves, and later we will see it is relevant for this type of dissipative coupling. Now, Michael and the students see that if you put the YIG in the anti-node position of the Kvt mode, as everybody was doing the experiment at that time, because you want to have strong coupling, then you see indeed this conventional coherent magnon-photon coupling forming Kvt Magnum polariton. Surprisingly, if you put the YIG at the node position, where the Kvt microwave field is very weak, then suddenly what they see is this type of level attraction behavior. This magnon and the photon mode in the Kvt as if they are coupled now by a kind of frictional force. And if you're changing the position of the yig at different positions, you can see the system goes from the coherent coupling dominated case to the case of dissipative coupling dominated, and in between these two coupling terms will effectively cancel each other as if there is no coupling in between. And the phenomena can be simply described using this very simple toy model, or two oscillators coupled simultaneously by spring and a dashpot, if you like. And you can tune in the Jaeger position to changing the spring constant. It took us almost 1 year until we understand the microscopic origin of this type of coupling. And we get a Hamiltonian, which I will explain to you later. It is essentially similar like this simple model here. You still have two oscillators with damping, the complex frequency here. And you have a coupling term J, which is essentially the coherent coupling rate, the Rabi frequency. And you have a coupling rate gamma, which is the dissipative coupling rate. There is one difference, is that there is a phase factor that depends on the direction of traveling wave of the system, which I will explain to you later. So how to understand that? Well, as I told you, the system, the Kvt system we have, including not only in the standing wave mode, but also a traveling wave mode. And this traveling wave has very important role in this kind of coupling. And suppose you have another mode, this Magnum. Now for simplicity, if you completely neglect the coherent coupling between the Kvt mode and the Magnum modes, you put them in the node position, for example, then the coupling you have is that both the standing wave and the Magnum modes, they both couple to the traveling wave. The traveling wave takes away energy from your system, and you can describe it using this coupling rate. And the full Hamiltonian that you can write is that you have a traveling wave, pk, you have Magnum mode, B-dag-B, you have Kvt mode, A-dag-A. Now between these A and B, you say I have no direct coupling. I set it as 0. However, both A and B will still couple to the traveling wave. And the coupling rate will eventually goes to these two rates, kappa and gamma. Now you can solve this Hamiltonian first by looking at the motion of the traveling wave. The operator of traveling wave, of course, depends on the operator of Kvt modes and Magnum modes. And eventually you can say this operator is a linear combination of A and B. Then once you solve that, you can plug it back into your original Hamiltonian, eliminate the traveling wave operator, then you get an effectively coupling between the Kvt mode and the Magnum mode. Now, interesting happens is that this effective coupling introduces an dissipative coupling between these two modes with a coupling rate capital gamma simply equals to square root of these two individual coupling rate, kappa and small gamma. This is the physics of this traveling wave induced dissipative coupling. Now, if I have confused you using this formula, here is an intuitive way to understand it. And I'm sure you all have seen this YouTube video. Now, you cannot hear the voice that I hear, but you can look at, you have different oscillators. They are randomly oscillating, and there is no coupling between them. Now, if you let the base also oscillate, as if it is a kind of traveling wave, goes between all those oscillators. Eventually, you see all those oscillators will get synchronized, as if between those oscillators there are certain kind of coupling induced by this base. Now, of course, this is a familiar phenomena. Already many centuries ago, Huygens already noticed this effect, and he called this effect as odd sympathy, because he noticed that if you have two pendulum clocks hanging on the same wall, even though between these two clocks there is no interaction, somehow there is a kind of sympathy between these two clocks. Eventually, the frequency will attract to each other, and then they oscillate in the same frequency. And if you look at different fields, this is what we call as dissipative coupling, induced by the traveling wave, as the model I just explained to you. But in other community, people see similar effect. In the optomechanical community, Asher Clark will call this effect as reservoir engineering. And in optical community, Sang-Hui Fan will call it as kind of non-orthogonal modes induced coupling. And quantum optical community, Garish at Texas, call it as base-induced entanglement. So these are all talking about the same type of physics where you have two modes indirectly coupled through a common base. And there are a few other groups also doing this kind of research in the Kvt Magnolic systems. And I will focus on this device in the next part of my talk. This is a device that you can put the order sympathy in good use. Now here's the device. You have a waveguide, sustained traveling wave. You have a microstrip, sustain the standing wave of Kvt modes. And you can put the Jaeger here, which you can have the Magnum modes. If you're changing the position of the Jaeger, you are tuning the coupling rates between those modes. So this is a very well-controlled system. Now, very interestingly, as I'm going to show you, this device will have non-reciprocal behavior, which means the microwave at certain frequency can pass this device only from one direction to the other, not reversely. And let's see the transmission measurement of this device. And here is the measurement. You see these two modes. If you're tuning the magnetic field, you're tuning the Magnum modes, and we are setting this coupling rate roughly equal, the coherent part and the dissipative part roughly equal, so that it looks as if there is no coupling, but coupling is actually there and very important. And you can see the coupling effect if you look at certain magnetic field. Let's say at this magnetic field, you scan your frequency, you get a spectrum. This is scanning the frequency at that particular magnetic field. Transmission from port 1 to port 2, S21. Now you see two modes. One very broad mode, this is the Kvt-like modes, and one very sharp mode. This is the Magnon-like hybridized mode. The line width of this hybridized mode is actually much smaller than the Gilbert damping tells you. That means this mode is indeed coupled photon Magnum modes. It's no longer Magnum modes. And in fact, if you look at the transmission at that mode frequency, the transmission actually goes to minus infinity, which means at that frequency, there is no transmission. And the line width actually goes to approaches zero, infinitely thin modes. Now that is the situation if you're sending your microwave from port 1 to port 2. Once you send in your microwave from port 2 to port 1, as I explained to you, you will have a different Hamiltonian with a different phase. This phase depends on the microwave traveling direction. And if you reverse the direction, this phase change a fraction of pi, a factor of pi, so that you get a different coupling. And now you still have two modes. And the Kvt-like modes look similar. The Magnon-like modes is completely changed. The damping becomes very large, and the transmission is no longer minus infinity, which means if you looking at the frequency of this Magnon modes, at that frequency, the microwave goes from port 1 to port, the microwave will not be able to pass the system because the transmission is 0. But if you do it reversely, sending microwave from port 2 to port 1 at the same frequency, now the microwave goes through. So you get a non-reciprocal device due to the combined effect. In fact, due to a kind of interference effect between the coherent coupling and the dissipative coupling that induce this giant non-reciprocal behavior, because the traveling from one port to the other port is completely invisible. Okay. So who cares about this type of non-reciprocal behavior? And in fact, many people cares about it. And if you do any quantum measurement involving a microwave devices, what you need to do is that put your device at extremely low temperature and let the microwave signal coming out to your electronics at room temperature to measure it. But you don't want to have any microwave signal going back to your quantum system to destroy the quantum states. So what you need is a very important device, which is called a circular, or you can also using an isolator. Basically, it's a microwave diode, allows you to let the microwave goes from one direction to the other direction. Now, if you look at the physics or techniques to build this kind of isolator or circulator, the physics is still the old classical physics of 1960s. It's kind of magneto-optical effect of bulk ferromagnetic material. And you need a large chunk of ferromagnetic material to have this isolating effect to allow you to have. And the device is bulky, expensive, because you need a large chunk of ferri, and give you limited isolation. And this is a kind of device, if you have never seen, you can buy it from Diode, the microwave company, at the price of about $300 to $500 for one piece. And it will give you isolation, which means the ratio between transmission from one way to the other way, roughly 54 dB. We measured this, we purchased the device and measured it. Now you can using this effect I just told you to make very different isolator. And this is the device made by my student Meng. It is already much smaller than what you can buy. And nowadays it's even getting smaller. Meng is improving it because all you need is a small, tiny piece of Jaeger sphere, 0.5 millimeter, very small. Put on the Kvt, let coherent and dissipative coupling do the work. Then you will have very large isolation. And in fact, you can even get infinity isolation. But the price is that you will reduce the bandwidth. And if you want to compromise the bandwidth with isolation, you have a lot of rooms to engineer your devices. The reason, as I told you, you can get almost infinity isolation is because the phenomena actually uses the physics of a singularity, which is produced due to the coherent and the dissipative coupling in the Kvt Magnolic system. And we all like singularity, right? Singularity is linked to infinity. And the most famous singularity fascinating to all of us is this black hole singularity. And in fact, our generation, I consider as a very lucky generation, because we can not only see the simulation of this kind of singularity, but we really now able to observe this type of singularity. What we cannot do now in our generation is to use this type of singularity, the black hole singularity. What we can use is this Kvt Magnolic Singularity. And here's an example which I'm telling you now, a device very similar to the device which I told you before, except it now has a new component. There is a small loop directly coupled to the Higgs field, so that you can locally control the radiation damping of the magnons. Then you can tuning the relative couple and relative damping, the ratio of the damping between Kvt mode and the Magnum mode. In the case these two modes have equal damping, if the damping rate is matched, then you see this perfect level attraction phenomena, as I explained to you. Basically, when you changing the magnetic field, control the detuning, you see these two modes getting attracts to a point that the eigenfrequency are completely equal, these two normal modes. Not only the real part of the eigenfrequency are equal, but also the imaginary part of the eigenfrequency are also equal if you set these two modes initially with equal damping. Now, very interestingly, if you look at the eigenstates, the eigenvector of the coupled system in this Bloch sphere, when you changing the detuning, what happens for the normal modes, these hybridized modes in such a system, is that both of the normal modes move towards the equator. And at this point, when these two eigenfrequencies equal to each other for these two modes, the two eigenvector actually meets at the equator so that they become parallel. That is the situation people know from optical community. This is the point this coupled system develop one type of singularity, which is called exceptional point, where the eigenvector are parallel, eigenfrequencies are totally equal of the coupled system. Now, more interestingly, if you further changing the detuning within this level attraction range, then what you see in the Bloch states is that Bloch sphere is that these two normal modes is going to moving along opposite paths on the equator towards the second exceptional point. One branch of these eigenmodes, this branch, actually goes through to additional singularity. At that two additional singularity, the hybridized mode has zero damping. The mode cannot decay in that system. It is completely bounded in your system. And that is what we call as a magnon-photon, bound states in continuum, which is a singularity where the damping becomes zero, and that is the second type of singularity you can produce in this coupled system. Now, I don't want to go in too much details into this singularity part of the physics. Rather, I would like to make an advertisement for one student and one former postdoc of me. Ying is going to next month give a talk. This experiment was done by Ying and Ipu. Ying is going to talk about that at APS March meeting, March 18. And Ipu, who is now a professor at Zhejiang University now, he is going to give an invited talk at Intermag in April, also about this coupling, induced singularity, and non-reciprocal behavior in the Kvt Magnolic systems. Now, that's all I wish to tell you today. Let me wrap it up. The take-home message number one is that I hope I have showed you that you can couple magnon and photon modes using coherent coupling. Just like you use spring to couple two oscillators, there you introduce a hybridized particle called Kvt Magnolic Polariton, and that's due to the fact of strong coupling. It's a very, very good transducer for you to connect in different systems. And this is still an exciting branch of this new field of Kvt Magnonics, and it's getting crowded. Many people is doing this type of research. So if you want to do something not so crowded, there is a second path, which I hope I introduced to you, less traveled, but equally interesting. You can introduce the dissipative coupling in this Kvt Magnolic system. That is as if you have a dashpot connecting two oscillators. And that will give you level attraction behavior that will allows you to introduce non-reciprocal behavior in this device. And that also allows you to create singularities in this coupled system. And this path is still very new. And if you would like to see more, and Ipo and I, we have just published one perspective article in Journal of Applied Physics, where we discussed a few possible future research in that field. That's all of my talk. Thank you for your patience. Thank you for your attention. And I hope we can find opportunities to work together in this exciting new field. That's it. Thank you.
Thank you very much for this very interesting talk. So this talk is open for questions. As you know, if you're on Zoom, please use the raise hand function if you ask a question. And if you are watching this on Twitch, please type in a question in the chat box. I will read it for you. And if you're on Zoom and if you prefer, you can always send me a private message and I can read that question for you as well. So the first question will be asked by Dr. Yi Li. Please go ahead with your question.
Hi. Hey, Can-Ming.
Good to meet you.
Excellent talk. Thank you so much for the talk.
Thank you.
So one of my questions is, so for the two type of dissipative coupling that you have introduced, one is that you have placed the X-sphere in a point that the coherent coupling is minimized in the cavity. That's your first paper, right? And then in your second paper to engineer this non-reciprocity, then you have actually the two cavity, as one is the microwave cavity, one is the X-sphere, coupled through a third transmission line of the microwave. So the second part I can understand. So but for the first part, I'm curious what do you think of the main mechanism for this dissipative coupling? Because I would say that, you know, if you place the X-sphere in a cavity at a point that there is no coupling to the cavity mode, where does the dissipative coupling come from?
Good. Yeah. Thank you for this question. I probably was not very clear in this part. In fact, the mechanism is the same. Short answer is. And the reason is this type of cavity we use is a special cavity. This cavity contains not only standing wave, but it also allows traveling wave. So this is also traveling wave mediated coupling for the dissipative part.
I see. Got it. Okay. Yeah, I missed that part. Okay. Thanks so much.
Yeah, I was not very clear.
Sure.
Okay, Dima, the second question will be asked by Professor Boschko. Please go ahead with the question.
Hello, thank you very much for the nice talk. I have a question about the new proposed model of circulator. So in principle, any existing circulator can be tuned to one particular frequency and have virtually infinite isolation. The reason they make it more broadband, that's why the isolation goes lower. But another important parameter for circulator is actually transmission loss. So what is the maximal maximal losses which you can achieve in your device? In other words, what's the minimal transmission loss?
Yeah, you're talking about insertion loss in terms
insertion
of
loss. Exactly.
Yes,
yeah.
Yes, and you can engineer it. The device gives you lots of freedom to engineer it. You always want to find the suitable device parameter you want to use. If you like to have high isolation, you set a piece of a group of parameters. If you want to have low insertion loss, you can also engineer it. The insertion loss is mainly determined by this transmission paths. And in this device, this experiment, the insertion loss is very high, minus 20 dB. That is not very useful. But in the device Mom made, he can get an insertion loss below 3 dB. So it's very low. You can also achieve that.
Okay, thank you.
Right. Okay, you're welcome.
Professor Hillebrand, please go ahead with your question.
Yeah, thank you, Can-Ming, for this very interesting work. I haven't fully understood what happens in the maybe very interesting intermediate regime where, let's say, so coherent coupling and the incoherent coupling become of same level. So what happens there? Where you are somewhere else on the Bloch sphere, probably.
Yeah. Professor, glad to see you. What's the time in Germany? I guess it must be very late.
Oh, it's 9. It's a quarter to 10 evening. Yeah.
Okay, good to see you. Yeah. Yes, you have the full controllability of the relative intensity. And in this device we use is actually exactly in the regime where the coherent coupling rate and the dissipative coupling rate are equal.
Oh, okay.
And there, if you just look at the real part of the eigenmodes, it looks as if these two coupling cancel each other, the coherent part and dissipative coupling, so that it looks like as if you have just a crossing of the two modes with a minimalized gap. This is because if you take the square, you have the J square and I gamma square will cancel each other.
Yes,
but exactly as you anticipated, that's not on all physics. The product term, which is I, J times gamma, plays the dominator physics here, introduce this exactly this non-reciprocal behavior, because if you reverse the direction of traveling wave, you change in this theta from 0 to pi. And that is the all physics is about.
Yeah, now I have understood. Thank you.
You're welcome. Yeah, that's exactly to the point.
Do you have any other question? I want to ask a quick question just for clarification. You mentioned the coupling due to the frictional force. So in the mathematical form, it's just that the coupling carries a phase, actually an imaginary part. And is that just due to because of the Faraday's law, the induction? So there's always a phase lag of the induced eddy current versus the driving magnetization?
It's connected, it's linked to that, but probably it's more easy to see if you look at this very simple model. You say, I have these two oscillator, between them I have spring, I have a dashpot. Then I have a spring force, which is proportional to the displacement. Spring force is Kx, x is theta. Theta is the degree of this displacement of the pendulum. Now, frictional force, for example, lens effect, is related with the changing of the flux. It is related to the velocity, if you like. And the velocity is the derivative of the displacement over time. Because the displacement is oscillating, you take a derivative, you get this phase difference of pi, 1/2 of pi, makes this coupling from the real component into an imaginary rate. And that is this phenomenologically to understand this dissipative coupling. It's as if it is a imaginary part contribution to the Rabi frequency, so to speak.
Right. Yes, thank you very much. Shulei, please go ahead with the question.
Hi, Can-Ming. Good to see you here.
Good to see you. Yeah.
I remember that a couple years ago you gave the talk at Argonne, and that time you didn't have the explanation for the level attraction. And,
I was discussing with your guys.
I'm happy to see the explanation. I just wanted to understand it. So you get a non-reciprocal effect in a system with the PT symmetry, but is this because, I mean, just want to think it in a general way, is this because your Hamiltonian is actually non-Hermitian, right?
Yes, exactly. Yeah. Okay. Once you introduce in this dissipative coupling, in this system, what happens, you have traveling wave, which takes energy away from your system. And this energy loss is exactly the reason for this coupling. So in the mathematical term, which means your system no longer conserves energy, the most important part of your system comes from the loss. And therefore, your Hamiltonian is a non-Hermitian Hamiltonian. And that brings all these physics. Exactly. Yeah.
Gotcha. Thanks.
You're welcome. Good to see you, Sule.
There's one question from the chat. I'm just going to read the question to you. Have you looked into the effect of the polarization of the microwave, if it is possible in your experiment, or maybe just in theory?
Yeah, neither. We haven't looked at this effect of polarization, neither in experiment nor theoretically, but it is certainly interesting to look at that.
It looks like we're out of question. We're going to have an informal discussion shortly afterwards. So at this moment, I want to thank all of you for participating.